This video will help you study for the Topic 1 test by going through each section that we've covered in class. You'll be asked to answer the questions at the end of each section and also write it on the paper you have to help you review. Let's begin. 1.1 had you identifying parts of the graphs, including piecewise functions. So remember, domain was the set of all x values a function can have. A range was the set of all y values a function can have. X-intercepts are where the graph crosses the x-axis. There can be more than one. Y-intercepts, there should only be one, and that is where the graph crosses the y-axis at. Increasing, decreasing, positive, and negative. A couple things to remember. Positive is when the graph is above the x-axis. Of course, negative then is when it is below the x-axis. Not to be confused with increasing. That's when the graph has a positive slope, and decreasing when the graph has a negative slope. One other thing to note, we would want to see a y-intercept in the form of 0, number, and an x-intercept in the form of number, 0. Domain and range we want to see in that interval notation with the brackets and parentheses. Try this problem. In section 1.2, we talked about transformations of functions. That was when a function was stretched, compressed, shifted, or maybe reflected. So we a lot of times said the parent function was related to as f of x, and a transformed function was some form of f of x. In a generic form, we could write it like this: a times f parenthesis bx plus c plus d. Now, I use a lot of basic jargon there. There's no numbers involved. But remember, this was when it's outside the parentheses, it's definitely vertical. This was a vertical stretch or compression. Remember, when it was the number in front by the x and multiplied, it was a horizontal stretch or compression. When it was a plus or minus, that was when it was a translation. So this was inside the parentheses, so that made it horizontal still, but it was a horizontal translation. Remember, being in the parentheses made the actions backwards of what you were thinking. And then this one outside, since it's outside, it was a vertical, and this was the translation, up or down. Use those notes and this graph and the choices up here to help fill in the correct colored circle from Desmos with the correct colored graph. Another practice from section 1.2, if we're given the absolute value graph as your parent up here, they ask you what might have happened if this was your transformed graph. Remember, on your notes, these numbers, either outside of the function notation or inside the function notation, give you special relationships to the parent function. Remember, if they're inside, they are usually opposite what you're thinking, whether that's a translation like C or a stretch or compression like B. If it's outside those parentheses of your function notation, then they are what you think they are going to be, but this one is your translation and this is your stretch or compression. Describe those transformations on this one. In section 1.3, we talked about piecewise functions. One thing to remember, you may be given a graph of a piecewise function and you have to write the equations. You'll see that's not what you're being asked here. But remember, these down here are the steps if you're given a graph and asked to create the piecewise. In this actual problem, you're going to have your very own blank graph, and you're going to need to graph each of these piecewise parts separately. Use Desmos. Remember how you might type that into Desmos. Here's a little reminder if you need it. Remember, you type the function followed by the squiggly bracket and the constraints on the domain, and then close the squiggly bracket. It will help you graph it. Give this one a try. Because this one's a little trickier to grade and give options for, we wanted to show you the final product for each of these functions. Note the color coding there for each particular part. Also, be very careful about open and closed circles. In section 1.5, we found the solutions to single variable equations and inequalities. Now, when it comes to single variable, that means there's only an x involved. Look at this equation right here. We only see x's. So when we're solving these, we used technology or Desmos to help us find them. Remember, if you're finding the solution, you're finding what x value you could plug into both sides of this equation, do the math, and get them to equal each other. Or, if you're looking graphically, when this equation on this left side is equal or crossing this function on the right side. Give this problem a try. In section 1.5, we covered single variable inequalities. Now, when I say single variable, that means we only have the x. For inequalities, that means instead of the equal sign, like you did on the last problem, you have the gators, or the greater than, less than, or equal to problems. So if you read this story right here, they're asking you to create an inequality that best represents the story. Go ahead and give it a try. Be very careful to note if it should have the equals to below your inequality symbol. Now that you've created the inequality, you might use that to help you solve the actual problem. Maybe you're making your own list and figuring out when she'll have over 70 pieces of candy. However you need to solve it, go ahead and find the answer to this story problem. Same problem here one last time. Now we want to know graphically how you would represent this situation. Use your inequality you created to help sketch the best graph. In 1-6, we built upon solving equations, but now we had double variable. That means we had x's and y's. Now we also had a system of equations. A system means more than one. So when we were asked to graph these, we would graph them and find where they would equal each other or intersect. We can graph them. We also gave you some tools to solve them by algebra skills. And algebraically, you would need to do this correctly in order to earn full credit on the test. Remember, this can involve the elimination method, the substitution method, or the same values method. With same values, that's something like where you'd get x equals x or y equals y for the equations and set them equal to each other. Substitution, you'd have one variable alone and plug it into the second equation. Elimination is when you stack them on top of each other and add them together and one of the variables eliminates. Remember again, this is you finding where both of these equations meet. Your answer, your solution, will not just be an x this time like it was in 1.5. It will be the xy coordinate where they cross. Try this problem. In 1.6, we knew there were two variables, and we tried the equations and the systems of equations, but we also tried a system of inequalities. We probably talked a little bit also about just one inequality in itself. For example, if you were just to graph this top one, you'd want to be careful. Now, Desmos can help you, of course, but if you were to plot the line, you would also know that it has a solid line. It's made of a solid line, and that is because of the equals to bar underneath, whereas this one is going to be a dashed line because it is not equal to. So when you graph both of those, remember, now we're looking at a region of possible points. There are many different combinations of xy points that could be plugged in and make these equations true, or inequalities true. So this time, our solution is not only one possible xy, but lots of xy coordinates. That's why we have to shade when it comes to solving these types of problems. Give this system of inequalities a try. To bring it all together in 1.6, we needed you to help create a set of constraints or inequalities for a real-world problem. For example, we had talked about mowing lawns and walking dogs on our example problem in our packet. You need to come up with a list of constraints or a couple inequalities with two variables and shade where they're true, and then the overlapping portion that's shaded is where your solution fits all of those constraints. Now that's a lot of vocab there, but maybe go back and look in your packet on the mowing and walking the dog one and compare it to this example where Amy's making jewelry. You need to set up constraints. Let's say, for example, $2.50 a bracelet. Let's call bracelets X. and $4 a necklace. Let's call necklaces Y. That way we have the same variables as each other. Note she has some limits. She can only make a total of 350 pieces, and she must make at least $800 for her new television. On this first part of the problem, set up some inequalities that are used to represent her scenario. Once you've set up the inequalities that represent the constraints in this story problem, remember X was bracelets and Y was necklaces, you'll want to make a graph for it and shade the zones, or the regions, if you will, that represent possible combinations of X bracelets and Y necklaces, where she'll make up to 350 pieces, but also make at least $800. Pick which graph represents this scenario best.